Hello Cloud Gurus and welcome to this lesson where we're going to be discussing data normalization. This is another theory heavy long lesson. I normally don't like going much over 10 minutes for a single lesson, but it wouldn't be effective to break this one up, so I'll try and stick to the key points and get you through as quickly as possible. So let's first talk about what data normalization is and why you might use it. Let's start with a quote. Normalization is a process which prepares data to be stored in a database. It helps establish tables and relationships between tables. It helps eliminate redundancy and inconsistent dependency. I've highlighted the key terms, but you may have gathered by the keyword relationships that normalization is used within relational database systems. As I'll demonstrate in later sections, the process isn't required with NoSQL engines due to how the data is stored. I'll go into more detail on why in a later lesson. For now, let's split the quote up into its parts. Firstly, the process prepares data to be stored in a database by helping establish tables and relationships between those tables. You will see in the upcoming slides that data stored on physical medium is chaotic. It's unstructured. There are repeating data sets and often inconsistencies and duplication, which only increases in line with its usage and the amount. Database systems aim to remove all of those things. As you have learned in the fundamentals lesson, the aim of relational database systems is to allow queries on structured data, to remove repeated data and inconsistencies, and to model the relationships between data. Physical data structures and relational database engines don't align, and normalization is here to bridge that gap. The process has another function. It helps you begin to take unstructured data and model the relationships in that data, something that may be obvious with simple examples, but once you go into the hundreds or thousands of fields, it can become complex, time-consuming, and prone to errors. Through the steps of normalization, it eliminates redundancy and incorrect or inconsistent dependencies between elements within the data structure. And I'll demonstrate this with a few common examples, a student system and an ordering system. In short, data normalization takes you from data chaos, which is complex and sometimes deeply unstructured data, and it helps you restructure that data so that it can be stored within a relational database system. The process transitions data through a number of states or forms, and these are known as first normal form, second normal form, and third normal form. Now don't worry about the names. During the next few slides, I'll step you through the process involved with each of the stages, and via some examples, I'll get you to the point where you're confident enough that you can repeat the process with your own data sets. So let's start with how physical data is normally stored, and we'll start with a pretty standard example, an order form. Order forms are a great example to use because they illustrate perfectly the complex nature of data that is traditionally stored within paper forms. My aim with this data is to transfer it into a relational database system. I want to minimize duplication, I want to remove data inconsistency issues, and I want to ensure the correct dependency of data. So let's spend a second looking at what's on the form. As part of my normalization process, I like to look at the structure of data that I want to normalize. Keep in mind that as you've learned in the chapter on database structure, the aim is that each row has a unique identifier. You don't want multiple items in any cell, and you want to ensure that the data is stored once and only once to minimize consistency issues. So let's deconstruct our order. The first thing I try to do is locate anything on the form that marks it as unique. The reason for doing so will become clear very soon, but I find that it makes sense to do this early. Sometimes this value will already be on the form, but often it's not. We know that each row in a database tends to be fully unique, and without a unique identifier for the order, this can't happen. In theory, the customer name is a possibility, but if their name isn't unique, then you will have problems. And even if they have an exceptionally unique name, what happens if the customer places more than one order? In many cases, the unique identifier needs to be artificially constructed and is often a number. You can imagine that the order number is already on the form, which may make things easier to visualize. The next thing I try to do is identify different types of data on a form, and these might be repeating or non-repeating. Let's continue with our order example. Firstly, we have the data which appears to directly map to our order. It seems that this occurs only once, and I've highlighted this in orange. Hopefully you're comfortable so far. I've identified or created something that is unique for this sheet of paper, our order form. Next, I've identified areas of the data I think occur only once on the form. Next, I try to look for areas that I think might repeat on the form. In this example, one order can have many order lines. These order lines can repeat as many times on the order as you have space for. And it's also worth keeping in mind that while in the physical world, the number of lines on an order is limited to the space on the paper, electronically, you could have thousands of order lines per order. The next point that I always try and consider is how data on the form is related or grouped. An obvious example of this is that in the physical world, the bill and ship to information are specific to the order. But that might not be what you want. You might want to allow the flexibility to bill and ship to different people for each order line. While this might not be the case, it's worth considering at the early stages. So let's look at how this looks in practice. Let's try and create a single database table containing our order structure. So straight away, I want to highlight a few things that will become apparent later. The first one is that we have multiple data items within one cell in an unstructured form. We actually have it twice per order, in the bill to and ship to addresses. Think for a moment how you would search for a name on an order, or search for all orders by that name when it's concatenated with other address information. The second is that we have multiple orders or rows as part of one order. And as we know from the database fundamentals lesson, this isn't possible within a relational database. One value for a primary key equals one row. One row equals one set of fields or attributes. In the above example, we have one order, and this has three sets of quantity, item number, description, color, price, and total. And this isn't going to work. So how do we resolve these problems? We use normalization, and we start by moving the data into this table into first normal form, or 1NF. So what is first normal form? Well, for data to be in first normal form, it has to satisfy a number of criteria. Firstly, the data is stored within a table where one or more of those columns uniquely identify an individual record, i.e. the table has to have a primary key. Although already covered somewhat in the above, there can be no duplicate rows or sub-rows. Each row in the table needs to be fully unique and identifiable by its primary key. And finally, you can't have column or row attributes which contain more than one piece of information. Now, strictly speaking, there is some debate on if this is needed for first normal form, but I always like to tackle it at this stage. It's easier. So let's step through how first normal form changes our data. I'll start with the table I had previously, and if you recall, I'd already suggested order number as the potential unique identifier for each row in the table. First normal form rule number 1 seems to fit here. The order number does uniquely identify each record in the table. Let's start by representing the data in its true form by flattening it. On the surface, it looks like I've made the problem worse. I've increased the data duplication, but this is actually a real representation of the data, as we can't have sub-rows in a database. And it's now clear that the order number doesn't uniquely identify a row. There are duplicates. However, I can see two columns which together identify each row uniquely, and they are the order number and the item number. I can combine these into a composite primary key for the table, so let's do that. Now that's much better. We also have rule number 3. The bill to and ship to columns are actually not atomic data types. They are actually a list of items, the street address, the town, and the zip code. It's always best practice to split those out, so let's do that now as a last step. And there we have it, a data structure which is in first normal form. It means there are no duplicate rows, that each row is identifiable in the table by the primary key. In this case, the primary key is a composite of order number and item number, and each attribute contains a single atomic value. Anyone with a keen eye may have spotted the attributes with the question marks in. Pay special attention to these in the next stage of normalization. They don't really fit in with the structure, they actually represent the greater order rather than for each item on an order. And I'll tackle these with the next stage, which is second normal form. So for data to be in second normal form, two things need to be true. Firstly, the data should already be in first normal form. Don't skip steps. As your skill matures, you may be able to move data straight to third normal form from physical, but that takes practice and I would not recommend it at this stage. Secondly, any attribute in a row needs to be dependent on all primary key values, not just one. Take a moment to reread this line. Any data needs to be dependent entirely on all primary key values in a row, not part. This is the first normal form table from the last slide, and you may notice that I've renamed some of the fields to make it easier to identify which is which. So we have order line total and order total. Now let's step through each of the columns and discuss their dependencies. We know that quantity depends on both the order number and the item number, as it's the quantity of that item on that order. So this column is already second normal form compliant and doesn't need to be moved. But what about description, colour and price? They are directly linked to item and not item on this order, so they have a partial key dependency. So these aren't second normal form compliant, and I'll tackle these shortly. Then we have order line total, and that's dependent on both keys as it shows the item price multiplied by the quantity. And it's just for a particular order for that item, so this can stay. Now the rest of the table, the remaining items are entirely dependent on the order number. They are global values for an order, not a specific line item on an order. So they have no place in the same second normal form table as the other data. So how do I resolve this? To illustrate how, I'm going to move the table around a little. I'm not changing anything but the order of the columns. The structure is the same. I hope it's starting to become clear what the next steps are. By arranging data visually like this, we've identified that our existing database table can be split into multiple tables. The first represents the order and contains only the data directly dependent on the order number. Notice how that only one row is needed in the table now, as I've removed data which repeats. And this is how relationships work in relational database systems. The second represents the items within our system. The table has the item number as its key and stores all dependent information. Crucially, it stores it only once. This means that if you have 1,000 orders which use a combination of these three items, you only need to store the item details once in the database. And this is one of the efficiencies gained via a relational database using normalized data. The last table represents the data remaining from the parent table, and this models the order line concept. Each row in the order line table contains the order number to which it references and the item number to which it references, and it contains any other information which depends on both, such as quantity and total. At this point, the data is compliant with second normal form, and it already starts to look much better. So what's next? Third normal form, and we'll look at that on the next slide. For data to be in third normal form, there is only one rule. No attribute can be directly dependent on a non-key attribute. So this is the order table from the previous slide. Note that it looks fairly logical, but let's add a few more orders by Joe Bloggs. So what would happen if Joe Bloggs placed all these three orders, but then wanted to change his shipping address? You might think it's easy to change with 3 orders, but what if you had 50 orders by Joe, and those 50 orders were mixed up in 10,000 for just one day? With large-scale, highly transactional and complex systems, this introduces potential consistency issues that we want to remove. Third normal form says that if there are any non-key attributes, and these are all non-key attributes, if any of these depend on another non-key attribute, then they shouldn't be in the table. So if any of these values don't depend on the order number, why are they in this table? To fix this, I migrate the non-key dependencies out of the table. Now there are a few ways to do this. The first is to follow third normal form exactly. We know that bill address, bill town, and bill zip depend on the bill name value. So an option is to make a billing table. Then we can adjust the original order table by removing the non-dependent field, like so. And that, strictly speaking, is third normal form, unless you have more than one customer with the same name, because then the ship name and bill name don't uniquely identify a row in the ship and bill table. To resolve this, much like when you created the order ID value, which if you recall didn't originally exist, you could make a billing ID and a shipping ID and use them instead of name as the unique identifier. And if you did, your data model would look something like this. A fully compliant third normal form table set. So let's recap. We've gone from this, a physical order form, to this, a structured set of relational database tables. A sensible question is, why do we do this? What's the point? Why put the effort in? So traditionally, why does anyone normalize data? Normalization is a process which was created decades ago when storage and compute was much more expensive than it is now. Cost was important as an overall metric. By removing data duplication, you reduce the database storage requirements, and since storage was usually a major cost component, the process achieved significant reductions at a time when this really mattered. By reducing the data footprint, you increase the amount of data which could be processed in a given time frame. Normalization improved integrity. By removing all data duplication, you significantly reduce the chance that the same record could be stored with different versions across your data schema. And finally, by storing data only once, you improve the speed or manipulation of data by your system. Imagine a system where customer delivery details were stored in every order record, where an update to this could mean updating 1 million records or more. Utilizing normalization, you split this up. Each record would have a foreign key, linking it to a customer record table. You would update the record once and have it impact all of the associated orders immediately. Normalization achieves significant operational efficiencies in early database systems. So like anything we do, there are some negatives to the process. It takes time and effort. Is it even still worth it? It might be simpler just to have unstructured data stored and throw more memory, CPU, and storage at it. It generates more tables. More tables equates to more relationships, which equates to more processing. And finally, queries become more complex as the server needs to handle complex inter-table relationships and data mappings. Well, that's the end of the normalization theory, Cloud Gurus. I thought I'd give you one more example to illustrate the process before finishing this lesson. Let's consider the example of a project management, control, and budgeting system within a business. Let's start by removing the sub-rows by flattening the data. Now, if you recall, I said during the first normal form stage, you could either find a suitable composite key, which made every row unique, or you could separate the tables immediately. I've seen both done and consider both correct, so this time I'm going to do the other option. Let's highlight the repeated data first. For a given project, there are multiple staff, and it's this repeating block which is causing our candidate primary key of project ID not to be unique. At this stage, one way of handling this is to make a composite key with project ID and staff ID, and this would make each row unique. But we did that with the first example in this lesson. This time, I'm going to split the repeated blocks off into their own table, which has the composite key. If we do things in this order, we end up with a project table, which contains all project-specific information, and a staff allocation table, which contains details of all the allocation of staff to projects. The tables are now in first normal form. We have no repeats. Every item is unique based on its row key value. The only thing I did differently with this example is, rather than creating one table with a composite key pair, i.e. project ID and staff ID, and leaving all data in that table, I pre-separated the data at this stage, an alternative and perfectly valid way to achieve first normal form. So what's next? If you recall, achieving second normal form meant separating any data which is not entirely dependent on all primary keys. As the project table only has one primary key, and as it's already in first normal form, it's automatically in second normal form. First normal form tables with only one primary key are always in second normal form, a useful rule to know. Let's focus on the project allocation table. And by now, you should be able to quickly spot the highlighted attributes are only dependent on staff ID rather than project ID and staff ID. To achieve second normal form, we split those attributes into their own table. So let's go ahead and do that. We start with our new staff table, and we maintain our project allocation table, but it now only has project ID and staff ID. Note it's perfectly fine and sometimes needed to have a table with just composite keys, and it's used to model relationships between two other tables, in this case our staff table and the original project table. So now the data is in second normal form. What about third normal form? You'll recall that the rule for third normal form is that no non-key attributes should be dependent on another non-key attribute. And you will see this is the case with the departmental name, which is only dependent on department ID, a non-key value. To fix that, we need to split the department name column into its own table with a primary key of department ID, and department ID becomes a foreign key in the staff table. And that gives us the following: our staff table, storing all specific staff information, with a foreign key which aligns with our new departments table. We have our allocations table, which provides a direct link between the staff table and the projects table. We've split up our original unstructured table, which repeats and has unclear dependencies, and via the process of normalization, we've ended up using 4 tables with structured data in a highly efficient manner. Well, that's the end of this lesson, Cloud Crews. I hope you've enjoyed it. Feel free to watch it again if you need to, as this is an important subject to grasp. If you do have any questions, or if you don't understand this topic, feel free to reach out directly or via the Cloud Guru forums, and I'll attempt to answer any questions you have. Otherwise, feel free to complete this lesson and move on to the next.